Section 2.4 is more lines. Specifically, we're going to talk about relating lines and direct proportionality. So we'll talk about parallel lines and perpendicular lines primarily. First, of course, is parallel lines. The key here is that they have the same m value, the same slope. So lines y equals 3x minus 5, y equals 3x plus 2, and y equals 3x minus 1 are all going to be parallel because they have the same slope. The 3 that is in front of the x is the same in every single one of these equations. The book refers to this as the coefficient of x, which really a coefficient is just a number that goes in front of that variable, and that's all they're referring to. So if they have the same slope, they're parallel. An example here, if I take those three lines and I sketched them for you, so I did the first one in green, the second one in purple, and the third one in red, you can see that obviously it's drawn by hand, so they're not perfect, but if you were to graph all three of these on your calculator, you would see that they're all parallel. The next step with that is finding a parallel line. So now that you know that they all have the same slope if they're parallel, how do you use that to determine a line? So if I asked you to find a line that's parallel to y equals 2x plus 5, that passes through the point to -7, you would have to extrapolate from that. Okay, well, the first thing that I need to account for is it says parallel, so that means that I need to ensure that I have the same m value. So y is going to equal 2x plus something. That's all I know, right, based on that first piece, because they're parallel. Now, if it's going to pass through to -7, then I can substitute the point into my y equals 2x plus b and figure out what b is. So -7 is my y value, so I substitute that in for y. 2 is my x value, so I substitute that in for x. I have -7 is equal to 2 times 2 plus b. From here, I can simplify, right? That gets me a -7 is equal to 4 plus b. Subtract the 4 from both sides, and then I get b. Oh, -11. So y equal to 2x minus 11 is a parallel line to y equals 2x plus 5 that happens to pass through the point to -7. Parallel lines are a little bit more straightforward. Perpendicular lines get a little weird, but it's not bad, okay? If I work with the line y equals 2x plus 3, right, I've sketched it here, I want what is perpendicular to it. So if you were to take this graph and rotate it to put the green line for the curve, for the line, y equals 2x plus 3, as though it were flat with respect to you, so you, right, and then you draw a straight up and down to approximate the perpendicular nature here, that's what you're aiming for. So the dashed line here is an approximation to what that perpendicular line looks like, just based on the sketch. A common guess for people is to think that the slope is negative or to think that the slope is reciprocal. It's actually both. It's negative and reciprocal. So what you're going to do is take the slope from the line that we have, which is y equals 2x plus 3, so that slope was 2. And then to get the perpendicular slope, which I'm denoting by m sub perpendicular, you're going to take the negative and then 1 over whatever the slope was for the other one. So if the slope is 2, like it is in the case of the line we have here, then the perpendicular slope is going to be -1/2. Well, now if we substitute that in the same way we did for the parallel line, we have we'll have an equation for the line that's perpendicular that'll be of the form y equals -1/2 x plus b. From that, you can choose any b and it will be perpendicular. If you imagine taking the highlighted dashed line here and just moving it up and down, it's still going to be perpendicular, because as long as you don't rotate it, it's still perpendicular to the green line in the graph. So b can be anything. Now, if we choose to make it go through the same y-intercept, we may select to choose the same b, which would be y is equal to negative 1/2 x plus 3. Now that should be exactly that dashed line that is in the graph above here. And in fact, it is, right? My next question would be, does the b value matter? Like, does it matter what I pick for b? Does it change whether it's parallel or perpendicular? I just said, no, it doesn't, right? B could be any b, and it will still be parallel or perpendicular depending on the choice of the slope. Whether a line is parallel or perpendicular to another line corresponds solely on the dependence of their m values. If the m values are the same, they're parallel. If the m values are negative reciprocal of each other, then they're perpendicular. Anything else, it's neither. We'll do a whole lot more of this hopefully in class so you can solidify it, because I do want you to get comfortable with parallel and perpendicular lines. The last thing is modeling direct proportionality, which I think you will find pretty straightforward. We're finding basically the linear model when b is 0. So all you have to deal with is y equals mx. Oftentimes you'll use other variable names, so that's what I said there in parentheses, but often with other variable names. So an example of this would be, you go to the grocery store and peaches cost $3 a pound. So find a direct proportionality model for how much the peaches you buy will cost. So what you do is you pick your variable names, right? I'm determining cost, C, so that will be my output, and the input is the number of pounds of peaches that I'm purchasing. Lots of P's. So if I choose C and P as my variable names for what was X and Y before, then C is my output, right, is going to equal that $3 times the number of pounds of peaches that I purchase. The concept to how to construct this you've already kind of been working with, but this just puts a name on it. This is direct proportionality. When you don't have that extra added term, it's just y equals mx effectively. Let me know if you have questions.